This video will walk through the wiring, configuration and bench testing of the main electrical components of the CNC mill. The electrical components will later be built into their permanent home in the controller enclosure, but for the moment we're going to concentrate on bench testing the components to ensure that they all operate correctly together. There are several stages in the bench testing, and we will do a progressive walkthrough, building complexity as we go as each stage is verified. The latest versions of the various wiring diagrams from Centroid can be found in the link in the description. And the final version for the completed controller box will integrate several of these together to support my specific hardware configuration, but that will show up in later videos. Starting with the simplest setup, we will verify that everything is initially powered up and working, and that the major components can communicate. The Acorn is connected to a 24-volt DC power supply, which provides a power indicator light, shown here. And then on this side, a flashing light indicates that the processor is up and running. So at least for the Acorn board, we're in good shape. The relay board is connected to the Acorn controller board to allow connection of output devices. The PC for the operator control application is wired to the Ethernet port on the Acorn. Shielded Ethernet cables and connectors are essential to avoid noise appearing on the line and disrupting the operation of the Acorn. Now we need to fire up the CNC12 operator control software. At this point, the CNC12 is communicating with the Acorn board, so we know that the basic configuration is valid. The 24-volt positive connection from the power supply is jumpered at the Acorn power block and provides a 24-volt output terminal, which in turn is connected to a 24-volt in connector on the input signal block, supplying power for all the input signals. The next test is to validate that the speed control port is sending a reasonable set of control voltages for the variable frequency drive, or VFD, on the mill. I currently have a digital voltmeter set up with the leads plugged into the output for the Spindle speed control. Set the range to read DC voltages. A voltmeter is going to be pretty much essential for wiring and testing configurations from this point in your build. The preconditions for the Spindle control test are that the Spindle maximum speed is set to 3000, with the minimum speed set to 0. If necessary, update and write those parameters, and don't forget to restart the CNC12 app after you're done. The script for the Spindle speed test is spindlebenchtest.cnc, which can be loaded with the F2 command. The calibration test works by sending a Spindle speed command and recording the output voltage generated. For a speed of 500 RPM or an S500 command, the voltmeter reads 1.68 volts. For a speed of 1000 RPM, the meter reads 3.36 volts. At a Spindle speed of 2000 RPM, we have 6.72 volts, and at 3000 RPM we have 10.07 volts, all of which fall within the parameters for the test, otherwise you'll be told that there's an issue. Take a look now at the Centroid wiring diagram for the Teknic SDSK motors. As you'll see, there are a bunch of individually wired connections terminating in the screw connectors for the motor control logic. There are some electrical requirements, including the use of pull-down resistors if you're going to be hooking up directly. By contrast, this is how the wiring is simplified using the C86 ACCP board. The board handles all of the electrical connection requirements, provides standard plugs compatible with the SDSK motor logic cables, and provides a simplified method of dealing with drive enablement, fault detection, and fault clearing. Each axis has an enable jumper that needs to be set to ensure the axis is active. The drives are configured, and here we have X, Y, and Z axes enabled. The A-axis is currently not going to be used until we get a fourth axis installed sometime in the future, so for the moment that one is left disabled. There is also an option to slave two motors together on either the X or the Y axis. This is for applications like a large router table, where you may have two motors driving a single axis. But in this case, there is only a single motor for each of the axes, so that jumper is left disabled as well. As it came, the mechanical support for the C86 ACCP was lacking a bit. It pretty much relied on the pins on the board being tied into the Acorn ports. There are a lot of them, so there's quite a bit to support the board, but I felt like it needed some better structure. So I designed a mounting bracket in Fusion 360 that supported the edges of the board and lined up with the mounting holes, but left all of the components free. The bracket is tied directly onto the base plate in the enclosure box, as you'll see later, so that we're not just relying on the pins in order to keep the board attached to the Acorn. If we flip the C86 board over, you'll see there is another set of jumpers for each of the X, Y and Z axes, which define whether the motors will be hardware or software enabled. As the board comes from the factory, all the motor enablement switches should all be set to hardware enablement. This means that the Acorn board cannot issue a software enablement signal for the motors. Instead, we're relying on hardware signals to enable the drives. This means we have to do a little more wiring in order to enable the Teknic SDSK motors, but it's a much safer option. You might just be able to see the text here, which indicates that this is a no-fault input. This is eventually going to be wired to the Acorn. But just for the moment, this wire jumper provides a constant no-fault signal and allows us to simplify the initial testing of the motor wiring. Here I am connecting the C86 ACCP board to the Acorn board. There are lots of pins and screw connections. This is a positive 24 volt rail and a common coming off the input power block for the Acorn. Preferably, you should use ferrules to terminate all of your wires, or at least solder the ends of the wiring to provide effective connections. Power up the 24 volt DC power supply to boot the Acorn again. But this time we are powering the C86 ACCP board as well. The red power LED lights up and the green heartbeat indication shows that everything is well so far. Next, it is time to wire up the motors to test their function. In this case, we'll be using the C86 board wiring option. It makes life so much easier. The SDSK motors are a closed-loop hybrid stepper. The drivers and the motors are integrated into a single package. The power for the motors will be provided by an IPC5 75 volt DC power supply, which provides ample power and deals with issues like back EMF generated by the movement of the axes and motors. We are also using the Power 4 hub option from Teknic. The Power 4 is a power distribution hub that simplifies the power cabling, but also provides an option for a 24 volt backup power supply to maintain the motor positioning across fault conditions. But we won't see that until the controller box is wired up and the motors are installed. Connect the power cable from the IPC5 75 volt DC power supply to the hub. And then each of the motors are wired to the 75 volt supply via the Power 4 hub. As you can see here, all of the control and data cables have been connected to the C86 ACCP board. This is what the Teknic SDSK motors look like. You can see the telltale LEDs indicating that they are on and ready to go. At this point, they're waiting for commands. And then, right next to each of those little LEDs, there's a USB port, which you can use to configure and auto-tune the motors. When they are shipped, these motors are configured for a no-load environment. When you connect them to the physical hardware, they can be auto-tuned so that they can adjust their parameters to deal with the weight and acceleration and environment you're operating in. We're going to connect to each of the motors and run up the motor control program from Teknic and demonstrate how it works. We've just plugged a standard USB cable from the motor back to the PC, and now we're going to run up the motor control application. The Teknic Clearpath motor control program is called MSP. I've already installed it, and the instructions to download MSP are pretty easy. The link for this app is located in the video description. In this case, we need to set up some particular values. You'll see that MSP has identified the NEMA 34 drive. It's the SDSK 3421P ELS2. Information about the Teknic's motor capabilities was described in an earlier video in the series, How Much Will Your CNC Mill Cost? And here we're going to change the drive resolution. When they come, the resolution is set to 800 pulses per revolution. And we're going to change each of the motors to run at a resolution of 6400 pulses, which is the preferred value for the enhanced version of SDSKs that I am running. We switch over the USB control cable to each motor in turn so that we can set up its parameters. We'll be back to utilize this motor control program in a later video to auto-configure the motors under load when they've been installed. The final smoke test is to prove that the motors will actually move. So we're going to do a jog test to verify that the motors will move correctly. Start up CNC 12, hit the reset, fire up the Acorn wizard. Hit F7 and then F10. And now we're going to verify a couple of parameters. For the drive access types, we've set these up to be Clearpath SDSKs. Acorn requires you to have an e-stop signal set up somewhere. So we're going to establish our e-stop as a normally open condition so that we don't have to worry about a physical e-stop switch. This is the default set of parameters for the Clearpath SDSKs. The max and fast jog rate should be kept at a conservative level. 50 is about as fast as we want to go for this test. None of the motors are fixed to the tabletop, so we don't want them to walk off the table. We set the overall turns ratio to 1. We're going to get a rotation of 360 degrees, or 1 turn, each time we jog the motors. As we don't have home and limit switches wired up at this point, we're going to use simple homing, so the machine won't seek the axes to non-existent home switches. Write the settings to Acorn. Close and restart CNC 12. Hit the reset, and then the cycle start to set the home for each machine axis. This puts CNC 12 and Acorn in a position where the operator can issue some movement commands. We can enter some G-code at this point to verify that we can get some motion out of the motors. This G-code moves the X-axis. In this case, it will be a single turn at a speed rate of 15. And then let's reverse the motor back to the start. And then we can do the same for each of the other motors. Alright, so we have liftoff. At this point, we basically have a functioning system. We are now at the point where we can wire up the e-stop and the no-fault processing between the C86 and Acorn boards and the status outputs from the drives. Earlier, I had installed a jumper on the C86 ACCP that ensured a no-fault signal was held high. So now, we want to use real no-fault signals. So the jumper needs to be removed, and the Acorn will be wired to provide a no-fault signal via the relay board. The relay is wired to the C86 board to provide the no-fault notification, and the Acorn board is powered up. However, there's no green light on the C86 board. The reason for that is we haven't yet enabled the output controlling relay 1. So that's what we're going to do next. I've now turned the relay board around so it is in the orientation that it will be when it is installed in the control box. We are now expecting to get a no-fault signal via relay 1. Only relay 1 is not currently configured. So we're in CNC 12. We're going to open up the Acorn wizard and then take a look at the output definitions. Grab the no-fault indicator and drop it into output 1. Write the configuration, and then CNC 12 has to be restarted, so let's fire it up. At this point, relay 1 is now turned on. However, we don't have a corresponding light on the C86. So let's go find out what that's all about. Alright, after a little insanity and confusing the relay numbering, we finally have relay 1 connected to the no-fault terminal of the C86 board. You can see that the green light for the heartbeat is now on. So we're in good shape. We're now enabling the C86 board based on the Acorn saying that there is not a fault with the drives. The next step is to use the C86 to provide a notification to Acorn that the drives are okay. On the C86 fault block, we are connecting to the common and then a normally open connector to input 5. So let's take a look at the input definitions. CNC 12 shows input 5 is configured as the drive OK indicator that Acorn is looking for. C86 will close this connection when it sees that the motor is OK. If the drive OK signal changes, the contact will open, and that signals the Acorn that there's been a drive change that indicates that there's a problem. So let's fire up CNC 12 again. One of the features of CNC 12 is a real-time display of the states of the input and output terminals. If you hit Alt-I, this will bring up the real-time display. Here are the input channels. We're showing that input 5 and input 8 are set, and that output 1 is also set. So what does that mean? Output 1 drives relay 1, and it's clearly on. So even though there's no actual jumper on input 8, we configured that to be normally open. And then input 5 shows that the C86 is indicating that the drive is okay. So we're in pretty good shape. Let's try to generate a fault by disconnecting the drive. So having just disconnected the data cable on this drive, we've got a cable fault. The drive OK is signaling a fault, so there's an indication to the Acorn that we've got a problem. So everything is working the way it should. Now it's time to wire in the emergency e-stop switch. This is configured as a single throw double pole. That is, there are two sets of terminals that can be controlled by this switch. So that's going to allow us to control two circuits. We're going to wire up one of those circuits to get this started. The switch is normally closed, so when it's in the out position, the contacts are normally connected and current will flow. When you hit the switch, it latches, the contacts are opened, and that's going to generate a signal through the Acorn board that says we've hit the stop switch. The only way to reconnect it is to twist it so it pops out again into its normally closed state. The e-stop runs from input 8. It's a normally closed mechanism so that when the switch is out, there is a connection that runs back to common. We had the e-stop configured to normally open on the Acorn board during the initial testing. Now that we have a real e-stop added to the circuit, we're going to change it to normally closed. We're going to wire this into input 8, which is the Acorn default for the e-stop. Run the common back to the common block for testing purposes. Let's power up the Acorn board with the emergency stop in and see what happens using the CNC 12 real-time I/O display. The switch is released at this point. Here we have a signal on input 8 indicating that the emergency stop is closed. Remember, this is the normal case. We now hit the emergency stop. Input 8 is cleared, indicating that the circuit is open. As you can see, we also lost input 5, indicating that there's a drive problem. If we re-enable the emergency stop, input 8 is back on, and so is input 5. Alright, so the emergency stop works. Well, that's the basic bench configuration wired up and tested. We're now in a position that we can begin to populate the controller case. The next video in the series will look at planning the controller case layout, modeling the 3D space, and building out the backplane.